Our last example for complex eigenvalues and eigenvectors is -1, -6, 3, -7. And let's tackle this and see how we go. Again, we're going to do it like we always do. -1 minus lambda, -6, 3, -7 minus lambda, and then we'll take the determinant of that and set it equal to 0. So the determinant of that, we get -1 minus lambda, -7 minus lambda, and then minus, looks like plus 18 is the number we get. And so as I look closely, I've got 7 plus 7 lambda plus lambda plus lambda squared. A lot of negatives going on here. Plus 18 equals 0. And so it looks like I've got lambda squared plus 8 lambda plus 25. Okay, so we've got a lot going on here. Lambda squared plus 8 lambda plus 25. So what am I going to do? Well, what I'm going to do is I'm going to come over and write out this, but I'm not even going to try to solve it equal to 0. I'm just going to use the quadratic formula right off the bat because that seems like the way to go. Okay, so lambda is equal to -8 plus or minus the square root of 8 squared, which is 64, minus 4 times 1 times 25, so that's minus 100 all over 2. So lambda is -8 plus or minus the square root, and this came out to be -36. Wow, it's almost like the number came out even. It's almost like I planned it. -8 plus or minus 6i all over 2. And so my lambda is -4 plus or minus 3i. So there is my there's my eigenvalue. Okay, so my eigenvalues are -4 plus 3i, -4 minus 3i, and so now I'll come over here and I'll try to find the eigenvalue that goes with one of these. So let's use the -4 plus 3i eigenvalue. I kind of like doing the plus one. It doesn't really matter, of course, though. Right, so as I find my eigenvalue, I'll take my first one, which was -1 minus -4 plus 3i, and then I will have -6, 3, and then -7 minus -4 plus 3i. All right, so there's that piece, and then this is equal to, looks like I get +3 minus 3i, 3, -6, and then it's -7 plus 4, so that's -3 minus 3i, and this is a 0 and a 0, and then we row reduce, and we know the whole bottom is going to become 0, so I'm just going to keep using my trick. 0 and then 0, 0, and 0. So here's how everything row reduces. And there we go. We've got all that, and now all we have to do is we just have to write out our solution. And so our solution is negative. Solution is -3 or +3 minus 3i x minus 6y is equal to 0. I could divide by 6y, 6. Maybe I should. Yeah, maybe I should. So that gives us 1/2 minus 1/2 I x minus y equals 0. That looks like that's going to be a lot prettier, doesn't it? And so this is actually equal to y. And so then I get my solution, which is x is my free variable, and x is equal to 1, and y is equal to 1/2 minus 1/2. And now I'm set up to write down my answer in terms of a P, C, and P inverse, and talk about what it means. And so what I've got is I've got my P matrix is 1, 0, 1/2, and -1/2. My C matrix is -4, 3, -4, -3. So I had to put AB and then A negative B. And then finally, for the last matrix, all I have to do is find the inverse of that. Let's see, the inverse of that, -1/2, 1, negative 1/2, 0, and then I've got 1 over the determinant, which is negative 1/2. So I basically multiply it all by negative 2. Okay, so that's going to make this a positive 1, make this a positive 1, and make that a negative 2. So I think that's the inverse. Sorry if I'm going quickly in these inverses, but we spent time on this, and I'm sure you're good at this. Okay, row times column is 1, 0. Row times column is 0 and 1. Okay, so there's that. Let me just check one more, just for the sake of it. Let's just check it one last time, just to make sure. You don't have to check these, but it's, as you can see, it's generally a good idea, and it doesn't take too long to check it. You just multiply it out and hope you get the answer that you started with. So negative 4 plus 3 is negative 1. Negative 6. Negative 3 minus negative 4, so that's a negative 7. And then finally, positive 8. Okay, and now row 1 times column 1 is negative 1. Row 1 times column 2 is negative 6. Row 2 times column 1, so we've got negative 1/2 plus 7/2. So that's 6/2 or 3. And then finally, I've got negative 3 minus 4 is negative 7, and it works out. So we were able to make all these work every time. Okay, let me come and just real quickly talk a little bit about imaginary numbers, and I hope this is informative to you and kind of helps motivate why we should think that complex eigenvalues might be connected, or why imaginary numbers might be somehow connected to rotations. And there's a real nice way of thinking about it. So let me pull out this one. And one way, when we think about imaginary numbers, the way we think about them is we often think about them as graphing them as having a real part and imaginary part. So this is complex with a 1 plus a 2i. And what you'll see is that if we go 1, 2, 1, 2, that this number means we went 1 in the real part and 2 in the imaginary part. And so that point, or that vector, is the vector we associate with the complex number 1 plus 2i. So we could think of 1 plus 2i as a vector, 1, 2, and that wouldn't be a really inappropriate thing to do. I want to ask ourselves a question. Oh, and by the way, this vector has a magnitude, right? So the magnitude of this vector is we do that squared plus that squared equals that squared. And so the magnitude of that vector is the square root of 5, because you've got 1 squared plus 2 squared. And so square root of 5 is the length of that vector. Okay. Now the question is, what happens if I square this thing? So what happens if I take z squared and I do 1 plus 2i times another 1 plus 2i? So what happens if I keep multiplying these by each other? Well, let's look at what I get. 1 times 1 is 1. 1 times 2 is 2i, and then 4i squared. And what you'll see is that I've got this actually becomes negative 4, because I squared is negative 1. So it looks like I've got negative 3 plus 4i. So what happened to my picture? Now I went 3. Now I went 3 in that direction and 4 in that direction. So now I'm pointed over in that way. What you'll notice, however, though, is if I put my original vector on here, my 1, and if I put my original vector on here, well, this angle, that shows up again, and it is actually the same angle that shows up right there. So every time you multiply by a complex number, it's the same as rotating by an angle, because these complex numbers, as you multiply, always end up rotating your matrix. And not only that, what is the magnitude of my new matrix? My magnitude, well, it's negative 3 squared plus 4 squared. So that's 9 plus 16 is 25, and take the square root of 25, and we get 5. So what happens is, when you multiply imaginary numbers, the imaginary number, the angle of the imaginary number gets multiplied, and it converts to your new one, and the magnitude of your imaginary number gets multiplied onto your new one. So if you have two imaginary numbers, and they look like this, and so if you have just any two imaginary numbers at all, and say the first one is right here with that angle, and the second one is right here with that angle. Well, if I wanted to multiply, say this is Z1 and Z2, and if I wanted to multiply those together, the way this works out, complex number-wise, is that you ended up getting a new angle, which is theta 1 plus theta 2. So you end up just adding those two angles together to get your new angle. And then this length is that length times that length. So maybe something like this. This length is length 1 times length 2. If that has a length 1 and that has a length 2, then that's your second length. So the lengths multiply to tell you how long your new vector is going to be, and your angles add to tell you your new angle. So complex numbers are inherently connected to rotations, and so that's why it kind of makes a little bit of sense here that that when we have complex numbers showing up in our matrices, it's connected to rotations. Additionally, so it's not meant to be that one of these motivates the other, so that they're two sides of the same coin. And after you study both subjects enough, you start seeing that they're actually saying the same thing. This complex number in real analysis, or in linear algebra, and this complex number in complex analysis are actually saying the exact same thing. Now, what's interesting, and what we'll talk about next time, is the length of these magnitudes actually matter. And so they are going to affect the long-term behavior of our matrices, of multiplying our matrices over and over and over again. So what we'll talk about in the very last section of the semester, which is next time, is going to be really fun. We're going to talk about trajectories, and that is what happens if you applied the same matrix over and over and over again, many times. What would be the long-term behavior? And that ends up being quite informative. And then we'll apply this idea of long-term behavior to a predator-prey system, and that is we'll think about we have a predator and we have a prey. Just by looking at their relationship, we can think about the long-term behavior and think about what's going to happen long-term with that predator and prey. So come back next time for the very last section in linear algebra.